In this scene, we're going to learn about the ExplosiaFX burn model, dissipation and diffusion settings. We'll start with the chemical burning model, which emulates real-world combustion, and then we'll change to the custom burn model and use sliders and curves to control our burn. We'll see how separate objects can be used for fuel and heat to create an ignition effect. Finally, we'll use diffusion and dissipation to customize the look of our flame and smoke. Okay, so here we are in Cinema 4D, and as you can see in the viewport here, we have this patch of oil in our viewport. It has a viewport material on it. And over here, we've got the XP system object burning oil. Now we're going to get to the other one called Bunsen burner a little bit later, but these are just props and setups that we can use to demonstrate the ExplosiaFX burn model. So taking a look at that oil patch a bit closer, you can see that it's made up of polygons, actually triangles, and then if we look on the underside there, we'll see that it's only one polygon thick. Now, because of that, I'll need to set the ExplosiaFX source tag up in a certain way. And so I'm going to select that tag. And if you look here, we've got the solid checkbox unchecked because it's actually just one polygon thick, and I want it to use those polygons as the source, and it'll give us a nice even distribution. To break up that very smooth even distribution, I've added a couple of noise shaders to our custom texture slot in each of the heat and fuel channels. Now, those are key. The heat and the fuel channels are key to a burn model. So what exactly are we talking about when we say burn model? Well, if we go to the ExplosiaFX object and we go to the simulation tab and we take a look here, we can see that we've got this buoyancy, and then the second one down, if we collapse buoyancy, is burning. And the burn model, currently the burning model is set to chemical. The other one is custom, and we'll get to that in a bit. But for now, we're going to take a look at the default, which is chemical. And of course, as the name suggests, this is emulating or simulating the real world phenomena, the real chemical reaction of burning or combustion. Now that reaction is in the real world, it uses several things. It requires a couple of components. It requires an oxidant, which is very commonly oxygen in our atmosphere, and a fuel. Then it needs an ignition temperature. It needs to be brought up to a certain amount of temperature for those two things to react. So we need the oxygen to react with the fuel, and then we get this chemical reaction. And once that's started, once we've ignited that, it's actually quite a self-sustaining reaction. And as long as we have fuel and oxygen coming back in, it'll continue to react. Now, this reaction is actually exothermic. As you know, when you burn something, it generates a lot of heat. So regardless of the initial ignition heat, it can exceed that quite significantly, and it then sustains because it's always above that ignition heat threshold. So of course, in ExplosiaFX, we are emulating that. We are simulating that with this chemical model. So when I hit play, we can see that we are adding fuel. Here's our fuel. So there's our oil, if you imagine the oil being the fuel. And then we are adding heat. So on the same object, I'm heating that oil up, you can think of it in that way, to the reaction temperature where the fuel will ignite. So the ignition temperature is reached. Now, we are not simulating oxygen in an explicit sense here because we don't need to think about that. We just know that this will ignite, the fuel will ignite at its ignition temperature, at its ignition threshold. So we don't need to think about oxygen. It's useful to understand that it's part of the reaction, but we only need to deal with the two components right now, which is the heat and the fuel. So back to that simulation tab, and you'll see we have a few settings here. We have a burn rate variation. Now, simply put, this just adds variation into each of the voxels over time, and it means that the fuel will burn at a different rate, a different speed. So it'll consume that fuel, generating the smoke and all that kind of stuff at a different rate. If I increase that quite significantly, you can see we get a very different looking burn. And you'll see sometimes it changes from a large amount of burn. So it burns a lot of the fuel immediately and it turns it to smoke. If I have it off completely, you'll see that we actually get a very consistent burn rate. And it's all going to stay the same, like so. I'll leave that at its default. And then we can look at this ignition temperature. Now, this is probably the most important of these parameters. When we're in chemical mode, this is the most significant change to our simulation. And if I decrease our ignition heat, you'll see not much difference. And that's because we're already burning the fluid. Everything is already at its ignition temperature. So let me increase that threshold or ignition heat all the way up to 1. And you'll notice now that we are only seeing the fuel. And the fuel, even though it's a representation right now that it's burning, it's not actually burning. It's simply being carried by the heat that we already have here. So when I'm playing, we don't see any smoke being generated from this burn reaction, because in the real world, that burn reaction is actually oxidizing our fuel, or the results of our reaction. It's oxidizing those, and that's what we often see as smoke. And what's happening when it's really hot is that smoke is generating, it's emitting photons because it's getting up to a black body temperature where it starts to glow, and then it cools down, and the darker stuff that we often see is the smoke particles. It's those oxidized particles. We're not seeing any of those in this particular reaction because we are not combusting at the moment. We are simply emitting temperature and emitting heat, and then that is being solved, but there is no burn occurring. Now, if I go back to an ignition heat of 0.5, we shall see that our smoke is generated and we are burning. So let me go back to the tag. And let's drop our heat value. Let's drop our heat value to below 50%. And you'll see now, we actually, for a starter, we don't have much buoyancy because we're not adding as much heat, but we're also not reaching that ignition threshold, that ignition heat. So what we'd need to do is if we wanted it to ignite, we would go back to our ExplosiaFX simulation tab and make sure that our ignition heat is below that 30%. And you'll see all of a sudden it ignites, it reaches the critical temperature where it ignites. Imagine the oxygen and the fuel reacting together, and then we start this reaction. We start this burning and combustion, and we then generate more heat, and it becomes this sustaining burning reaction. So that's really powerful because we can create all sorts of different real world effects. We can even animate this ignition heat, so you could have it much higher at the beginning, and then you animate it down, and as you animate through to the point where it will ignite, you get this ignition and all of a sudden combustion occurring. And so the last parameter we have here is max heat. Now, what exactly is this? Well, this is the max heat that can be added to a voxel within our ExplosiaFX simulation. So we're actually capping the amount that can be added from our source object. Now, of course, because I've put it lower than our ignition heat, that means that we cannot get to our ignition heat, and therefore it would not ignite. So we can actually use this. We could leave the ignition heat at a steady amount, so let's say 0.5. Let's make sure our tag is adding a lot of heat. So let's put 100% heat in. And then we go back to our ExplosiaFX object. You'll see not much changed there because we've capped it at this really low value. Now you'll see as I increase it, the heat will be able to increase from that source. So it's able to add more, but it's still capped at this 0.38 times our 100% that we're adding in the tag. And I'll increase it, and now it's over the ignition temperature. And so we'll actually get that ignition occurring. So you can see we can create some really cool burning effects here just with these few sliders, combining that with the knowledge that the heat is the key thing here. It's the key thing that will cause the burn and create the ignition moment and the combustion. Okay, let me reset those. Next, we're going to look at the custom burn model. And we can choose that from our burning model drop down here. We can go custom, and you'll see that we get several new parameters exposed. We still have the original ones. We still have burn rate variation, ignition heat, and max heat, just as we did in chemical mode. But we also have these new ones. We have burn rate, heat production, smoke from heat, smoke from fuel, and gas expansion. Now you'll see that we have these values input. We actually have some preset values, 73 for burn rate, 90 for heat production, and then 1 for the rest. And we also have inside these twirl downs, these sliders have twirl downs, we have this multiplier spline. So all of these presets, they might seem a bit arbitrary, but they're actually there to closely match our chemical burn model. So if I hit play, you can see we get our burning, and it's very similar to how we had it with our chemical model. Now it's not exactly identical, but it's a very, very close approximation. And it'll actually also help us explain some of the properties of our chemical burning simulation. So what do we have here? Let's look at our first parameter. We have the burn rate. Now, of course, as the name suggests, this is the amount of fuel that is burnt per second. So in each voxel, we have a certain amount of fuel, and per second, this is the rate at which it will burn. And our spline here is a multiplier for this value here, this 73 burn rate. So we're going to consume 73 units of fuel per second inside those voxels. But we're also making sure that it multiplies a curve based on that density. So it's not a constant 73. What this is telling us, this spline, is that the y-axis is the burn rate value. So that's the 73. So we can think of this as 0 to 73 up here. And then we have it dramatically drops off. And then along the x-axis, this is the amount of fuel, the density of fuel within our voxel. So 0 here and then 1 at the right side here. So what that means is that at the very beginning, where we have 0 fuel in our voxel, our burn rate is essentially being multiplied by 1. So our burn rate will be 73. Then if we move down this steep slope that suddenly drops down significantly, we see this one down here. And if I expand this out, we'll see the actual values. We can see that on X, which is the fuel, remember X is the fuel, 0.08. So that's a very low amount of fuel, about 8% of fuel. And then the point on the Y is 0.11. So it's about 0.1. So 0.1 times the 773 becomes 7.3. So the burn rate, when we have 8% of fuel in our voxel, becomes just about 7, between 7 and 8. Now, the reason for that is emulating that real-world burning model, remember, is if we think about this, if there is fuel occupying a space and it's at its most dense, the most dense it can possibly be, it won't be allowing any other substances in that area, no other gases. So what will be occurring there is that there will be no oxygen. So we can't actually have a reaction occurring, and our burn rate is really low where there is a lot of fuel, but it's extremely high where the oxygen can get in with the fuel and mix with the fuel. So you get this nice oxidation, you get the combustion, and it's just allowing enough oxygen in and enough fuel, and there's the right balance, and we get this ignition occurring. So, like I said, the burn rate is the rate at which it will consume the fuel. And if we just make it constant, so I'm just going to get rid of our points on our spline here, and I'm just going to make a straight line just to make the point that now this is going to behave as a constant. So it's just whatever the fuel value is, whether it's 0 to 1, it is always going to multiply our burn rate by 73. So if I now press play, we'll see that everything, no matter how much fuel is in the voxel, it is burning at a rate of 73 fuel units per second, which is very fast. And so we're barely seeing any of the burning fuel, any of the burning oxidized fuel. So if I drop this down, we'll start to see that's more fuel. Well, even there, it's quite consuming a lot. So right down, I'm now doing just 5 units per second. And we're actually seeing some of the fuel now and less smoke being produced. Less combustion is occurring, less burning is occurring. So the slower burn rate means that we can see more fuel. And if I drop it right down to say 1, our smoke production will be much later on, because if you think about it, it's not burning, it's not creating much heat, and the fuel is still there, so we get much less smoke. Okay, so I'm going to reset that back to its chemical default, and let's have a look at the other settings. So of course, burn rate variation is simply going to be adding variation into this value. So essentially we are giving it a natural variation, because there wouldn't be constant amounts of oxygen. That would slightly vary in density, and you get these nice burn variations. So that just makes it look a little bit more natural. I'm going to leave it at the default at the moment, and let's take a look at heat production. Now, in exactly the same way as the burn rate multiplier works, we are using the y-axis here to multiply this 90 value, and then this is also fuel density again. So 0 to 1 means that we get a multiplication, so that if we have, say, half fuel, 50% fuel density inside our voxel, multiply it by around about 45 heat. So it's going to generate heat of 45 per second into our voxels. So this is essentially control over our exothermic reaction. Remember, as the fuel and oxidant combine, they reach their ignition temperature, they then start producing their own heat. The reaction is exothermic, it gives out heat. So the production of that heat we can control with this spline here. And of course, if I drop this down, we're essentially multiplying the max here of 90. So we could have it, not produce any heat at all. And it would just essentially, it does not increase any heat. So we might not get any expansion. The buoyancy might be not very exaggerated. And then it's relying on that initial heat being added to our simulation. Now, we've talked about the fuel, the burning of the fuel, and then the heat production, of course. Now, the smoke that we see generated, of course, we are not adding any smoke to our simulation from our tag. So if we select the tag, you can see that smoke is set to 0%. So of course, because we are burning our fuel, we are generating smoke. And you can see the next two are related to that. So we have both smoke from heat and smoke from fuel. Now, these are directly related. They require each other to create smoke. So essentially, if we have no heat, we will not be generating any smoke. So we've got just fuel and no heat, we won't be generating any smoke at all. And vice versa, if I have a multiplier of 0 on any of these two and not the other, you'll see that it just doesn't produce any smoke at all. What we can do is we combine them, and you can change the amount of smoke that we are seeing produced. Now, remember, when I increased our burn rate, we were producing a significant amount of smoke. So if I make our curve a little bit more gentle here, and we'll see that we'll get more smoke as I increase the burn rate, like so. What we can do is we can actually reduce this amount of smoke. You can see it's very dense there. Is I can drop that down, and we can combine these two multipliers, and we'll get much thinner or finer smoke depending on our fuel density and our heat. So there we go, we get a bit more wispy smoke, but it's still consuming a lot of that fuel. It looks a bit unrealistic perhaps. And let's reset our burn rate curve. Get that back to a natural looking burn rate, like so. And then our last one here is gas expansion. Now this one's really useful. If we are creating a lot of heat, in reality, that gas would expand. It would all of the energetic molecules in our smoke and fire here would be creating an increase in pressure, and it would be expanding, pushing the surrounding air out the way. And so we control that with our gas expansion value over here, set to 1 by default, and the spline is actually set to a constant. So it's regardless of how much burning fuel we have here, what the burn rate is, the gas expansion will remain constant. Now, if I hit play now and I increase our gas expansion, let's go to 200, you'll see that the top of our fluid here is expanding quite a lot. And this is exactly what it does. It increases pressure. So the more heat, the more burning that's going on, it will increase the pressure within those voxels, causing the fuel and smoke to disperse and heat as well. So it's actually causing advection of our fluid outward, caused by the pressure of our burn going on here. So it's expanding our fluid out. And this is obviously very useful for things like explosions. And we could possibly use this for, if we animate this up. So if we start at 0, we play a few frames, maybe up to just a very short 20. We make it extreme up to 500. And then we animate it right back down to just 1, which is the default sort of atmospheric pressure perhaps. And you'll see it expands very quickly, and it continues on that expansion until I actually animate that back down again. So we get this sort of expansion of the fluid very quickly, it's burning very quickly, and then it calms back down again. But it's a good way of creating larger volumetric simulations. So we want to perhaps fill a volume really quickly, we could use the gas expansion value. And just like all the splines, this is the x-axis here is the burning fuel. So if I set that to let's set our expansion quite large here. This is essentially saying the most expansion will occur at higher fuel values. So if there's more burning fuel in this end, expand it more. So that can give you a nice looking effect. If you look at the beginning, we're not expanding at all. And then as soon as they start burning the fuel, so it's not just fuel that's unburnt. It's when the fuel starts to burn, then it increases the expansion values. Okay, so that's our custom burn model, which obviously allows us to burn our fuel at different rates, generate heat at a different rate, different amounts of smoke, and then obviously our gas expansion. Now there is one more thing to look at directly related to our burning model, and specifically our ignition heat. Now if I go back to our chemical model, just to keep things nice and straightforward, we've got this ignition heat currently set to 0.5. Now of course we're exceeding that 0.5 because we are adding heat from our oil patch source over here. So when I click that tag, you can see we're adding both the fuel and heat, and those are the two things required for us to create this combustion, to create this burning reaction. The thing is though, is that we don't need to add the heat from the same source object. So what I could do is I can zero the heat out, and if I play now, of course, there's no combustion occurring. There's no heat to carry the fuel upwards with that positive buoyancy, and therefore our fuel is negatively buoyant and then it falls downwards in the sim. So what we can do though is we can bring that heat, that ignition heat, in from a different location, from a different source. So I'm going to grab a sphere object, I'm going to shrink it right down, and I'm going to put it in our sources folder here. Then of course I'm going to right click and I'm going to add an ExplosiaFX source tag. I'm actually going to move it over to the right here. Oh, sorry, the left, and I'm going to hit play. And you can see right now that it's just at default. It's generating its own fuel, it's generating its own heat. It is then burning and creating that smoke and all of the other properties that we get from the burn. If I go to that tag, I don't want to add any fuel, so I just want to take the fuel off. I'm going to leave the curl on, and maybe I'll increase the pressure so it's a bit more expansive. And I'm going to have I'll have the velocity active as well. So we're not currently seeing anything at the moment because most of the stuff coming off this sphere is in the temperature channel, and we are not viewing the temperature channel. We can display that in a second, but first of all, let's bring that heat from the sphere into contact with the fuel on our oil over here. So if I bring it in, you'll see we hit it here, and all of a sudden we are igniting, we are bringing the temperature high enough, the heat in, and it's igniting our simulation. So we're actually getting that combustion occurring. So this is really cool for creating these interesting ignition effects, all sorts of cool stuff like that. Okay, and I can bring it back in and we get the same. So I'm adding the motion into the simulation as well. I'm sort of pushing it around, and that's causing this combustion. So the principle there is that we don't need to use the same object to add the heat to our simulation to create our burning. And like I said, that's a great way of creating all sorts of cool ignition effects. Okay, so we're done with the burning oil system for now. So let's turn everything off. And I'm actually going to deactivate the tag in the oil patch, just to make sure it doesn't interfere with our one over here, our Bunsen burner. And let's activate that and turn everything on. And you'll see straight away in the viewport, we have an approximation of a model of a Bunsen burner. And when I hit play, you'll see that we have a flame being solved in our calculation here in our ExplosiaFX object, and it is burning, it's generating fuel, it's generating heat, and that is then combusting and creating the smoke that you're seeing. So what are we doing in this setup? Well, we're actually going to look at a couple of settings in the simulation tab that really can change the look of your flame and your smoke and your fluid motion. So we've looked at burning. We're now going to look at the diffusion and dissipation. So let's look at diffusion first. Now, quite simply, the diffusion is going to diffuse our properties. So whether it be smoke, heat, fuel, and then this one here is called viscosity, but it's actually diffusing our velocity. So all the channels, the major channels that we're used to seeing here, if I diffuse those, they are going to soften. They're essentially going to diffuse a certain amount of their property out into the next voxel and then repeat that process. And you'll see that we actually end up with a softer looking smoke. It's a very similar process to blurring pixels, and we actually end up with a softer looking simulation, a softer looking fluid sim. And you can see as I combine different parts of these, so if I diffuse the heat, if I diffuse the smoke separately, but I leave the fuel undiffused, we get this kind of sharp fuel area, and it looks very nice. And the combination of these can give us all sorts of different looks. And a diffuse flame like this, or a diffuse simulation like this, you'd very commonly find with things, small scale things such as candles, your stovetop if it's a gas hob, that kind of thing, where you need to get a really smooth looking flame. And the diffusion parameters here will all help with that. Now, like I said, the viscosity parameter diffuses the velocity. So if I put that to 100, you'll see that the overall simulation, everything, the resulting velocities are all dissipated and, sorry, not dissipated, they are diffused, softened, and that actually reduces the overall detail of our simulation. You can go extreme with that one, and you'll see that we get a much sort of slower simulation, as if it's thicker, and we lose all the detail. So let's drop those back to their defaults and make sure we're getting back to our nice, perhaps nicer looking, broken up, vorticing and interesting looking motion. Next up, we have the dissipation settings. Now, these are really powerful, and I probably use these on every single project. And this is how we can essentially say how much of the fuel, smoke and heat and all of those things dissipate into the atmosphere around them. They actually move away from the burning. So essentially, imagine we've got our smoke. It's the resulting oxidized molecules in the air there, and then they're really low density, and we can force them to dissipate. So we can actually have them over time reduce the amount. So essentially, this is a rate value. So we're going to lose this amount per second. And you can see I've reduced the amount of smoke just by using our dissipation. And it looks really excellent because you can really dial in the look of your smoke or flame. And just like that with our other channels, we have our heat dissipation. Now this is essentially, you can think of this as cooling, because of course we are reducing the amount of heat over each frame being added. So it'll actually decrease and decrease and decrease, eventually dropping down to nothing. So we could actually have it cool extremely fast. And if we do too much, we might not even get any burning, but you can see that it's creating all these different looks just by tweaking our dissipation settings here. We can actually go above the 1 value, but of course, if we go above 1, very quickly our fluid just completely vanishes. So if you've got a lot of one of these channels being added, now smoke can't actually go above 1. So if the smoke dissipation is above sort of say 10, it's going to really rapidly remove that from our simulation. Okay, so then of course we've got fuel dissipation. Now if we do too much fuel dissipation, of course we're going to reduce the amount of fuel really rapidly. And if I go extreme, like so, we barely get any flame at all. We get much thinner smoke as a result. We get this nice wispy looking smoke. So that's cool. And then we have this other one here called fuel ambient. Now, fuel ambient is actually a minimum value of fuel. So imagine the fuel inside each voxel. It's the minimum amount of fuel that will actually dissipate with the fuel dissipation parameter. Now, that sounds a bit strange, but if I put some settings in here, and we've got our fuel dissipation and we have our fuel ambient, essentially any of the values smaller than this value, so any values below the 50% value, will not be dissipated. So essentially what that means is we will only be dissipating fuel if it gets really thin. And if you look here, I can obviously exaggerate that, but what this does in combination with the fuel dissipation, you'll see that it dissipates higher up here. In fact, let's get rid of our smoke for a second. In fact, we can just dissipate that. There we go, get rid of our smoke nicely. And if you look at the top here where our fuel's getting really low, and if I drop this down, the threshold at which the fuel dissipates is a larger amount. So everything below this value, 0.5 right now, is protected from the dissipation, but anything above it can dissipate. Okay, so there we go. That's a real nice way of dialing in your look again. Now we have something called velocity damping, and I'm going to put the dissipation of the other channels off again. And what we'll do is we'll put the velocity dampen to 10, just to really exaggerate this. And you can see where all of the velocities, including the buoyancies, everything like that, they are being dampened over time. So they eventually, they still move upwards, but they are being significantly dampened. So this is actually, imagine this as a dissipation of the velocity channel. This is especially clear when we look at the speed of our simulation, and we can do that in our display tab. And if I look at the speed, you'll see we're getting really low values down here. And if I turn that back off again, you'll see that our fluid can move through its full speeds, and we're seeing some reds and yellows there. But as I increase the damping, it really decreases the speed of our simulation. And that's just good. If we're getting really erratic simulations, we might want to calm them down. The velocity damping is a really useful parameter for that. Okay, so there we have it. We've looked at the burn model in the simulation tab. We've looked at the very cool dissipation and diffusion parameters that can really help us shape our fires, shape our flames, and our fluid simulations.